Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Kumar Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. So do watch this session. If you like it, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. All right. You can also visit our website www.we-learning.in. Whatever sessions you are getting here, you will be getting all the sessions there. Along with that, you will be getting session notes also for each and every session. All right, do check it out. Now, without any delay, let's get started with today's session. We were doing current electricity, and this is lecture number 10. So far we came. Concept-wise, if you see, this is going to be the last lecture. All right. But after this lecture, there will be two more sessions where we'll be seeing numericals based on this entire chapter. Anyways, we have done a lot of questions. On every concept, we have covered the questions, right? But still, some extra questions are there, which we'll be seeing in the numerical part in the next two sessions. All right? Fine. So in this session, we are going to see meter bridge and potentiometer. So these two things you would have seen in your laboratories, in your lab. There are experiments also based on these two in your course, right? We'll be understanding how to use this and what are these used for. Meter bridge. Meter bridge is something which is used to calculate unknown resistance, to find unknown resistance, okay, in the circuit. And potentiometer, from the name only, potentiometer, right? It is used to find the potential difference of any cell or any resistor if you have put there. Fine. Now, let's see. First, we'll discuss meter bridge, then potentiometer. In detail, we'll see everything properly with construction. Okay? Just take out your notebooks and pen and get ready fast. It's going to be very interesting session. You have to do it on your own only. I'll just tell you the concept, the way how to do it. Okay? Now, it is an electrical instrument which is used to measure unknown resistance, and it works on the principle of Wheatstone Bridge. Only two things you have to remember in meter bridge. Two things, very important things. If you are writing this definition, underline measure unknown resistance. First thing, it is used to measure unknown resistance. Second, it is based on the principle of Wheatstone Bridge. All right. I hope you remember Wheatstone Bridge. Okay, let me just remind you. So there were four resistors connected, something like this, right? Correct? It is not properly. Now it is looking fine. This, let's say this is R1, this is R2, this is R3, this is R4. Now this is connected to some part of the circuit. Fine. Now Wheatstone bridge means if the bridge is balanced, then R1 by R3 is equal to R2 by R4. The ratio of these two resistances will be equal to the ratio of these two resistances. This is when balanced, right? This was the Wheatstone bridge. Now what happens when it is balanced? Basically, if let's say there are 4 points A, B, C, D. Balance means the potential of C and D are same. Balance means C and D are at same potential. All right. C and D are at same potential. That means if I connect a wire also here, there will be no current which will be flowing in this. If I put a resistor here, nothing will happen to it. If I put a capacitor here, no charge it will get. Clear? C and D will be at same potential. Same potential means current only flows from higher potential to lower potential, right? If the potentials are same, there will be no flow of current. So here there is no flow of current. That means if I attach a galvanometer here, if I connect it, galvanometer, I hope you know, it is a device to detect the presence of current. Very small amount of current you can measure also, but basically we use it to detect the presence of current. If you want, you can write down galvanometer, used to detect the presence of current. Clear? What happens if there will be current? This will show deflection like this, like this. All right. If there will be no current, then there will be no deflection. Now here, since there is no current in C and D, so there will be no deflection. If there is no current, since C and D are at same potential, you can say if R1 by R3 is equal to R2 by R4, there will be no deflection. Very important, this no deflection is very important, because the questions what we are going to get from this will be based on no deflection. In meter bridge, even in potentiometer also, the questions what you are going to solve will be based on no deflection. Okay? And any value which we are measuring by the method of no deflection method we call it, or we call it null point method. Okay, I'll tell you what is null point. So there we get more accuracy basically. Okay, if you want you can note it down. Done. Now let's see the construction of meter bridge. So from name, if you understand, see bridge, you can relate it to Wheatstone Bridge. You will remember, oh, meter bridge was something which was working on the principle of Wheatstone Bridge. Now meter, somewhere this meter has to be there, no? Basically there is a long wire in it which is 1 meter long. This wire, if I write about this wire is 1 meter long, or we can say 100 centimeter also. Usually everywhere it is given in centimeter only. 100 centimeter. Okay. If I put a scale and measure it, it will be 1 meter or 100 centimeter. It has to. Now, second, the material by which this wire is made should be alloy. Made of alloy. Why? Because if you remember, I told you alloys are something which are temperature independent. The resistivity is temperature independent. I don't want the resistance of this wire to change as the temperature increases. See, we are going to do experiment. In experiment, we need accurate values, right? Now, when the current will flow, no doubt the heat will increase. If the heat will increase, what will happen? Temperature is changing, the resistance will change, our value will keep on changing as the time is going, right? So we need that kind of wire in which the resistance should be independent of temperature. That's why we will be using some alloys. If you remember, I told about nichrome, I told about manganese, I told about constantan, right? These kind of alloys you can use. I'll write manganese, constantan, nichrome, etc. Any alloy which resistivity is independent of temperature, you can use that. Fine. Okay, why I need this, I'll tell you. See, first thing, I want the resistance should not be changed. Alright. Any other thing about this wire? One more thing. The cross section of this wire should be uniform. Cross section area. Uniform cross section. Uniform cross section in entire wire. Clear? Because if the cross section is changing, resistance changes at every different point, right? R is equal to rho L by A. Cross section changes, resistance changes. I want at each and every point the resistance should not change. Clear? So these three are the main qualities, characteristic of this wire which we are selecting. Then we will connect it with, these are plates, metallic plates. Okay, these are, I'll write here, metallic plates. Basically these are copper plates. Okay, I am writing metallic plates because in NCERT it is written metallic, but basically we are using copper plates. Fine. It's a good conductor of electricity. We want the electricity to flow in this entire thing. Now these two places which are empty, we'll be connecting resistances. This is one resistance, this is another resistance. Any one resistance will be unknown, any one resistance will be known. Let's say this is resistance R, which is an unknown resistance, which we have to find out. Okay. Unknown resistance. Now this is something which we have to find out. And this will be known resistance. Basically, we do not connect a resistance here. We connect a resistance box. Resistance box. What happens in that resistance box? A box will be there. You would have seen in your lab. There will be pins like this. Okay. You remove the pin, that particular resistance will start working. That way it is. Okay. So there are 3-4 different kind of resistance will be there. Different resistance, different values of resistance will be there. Whichever value you want, you can set that particular value. Okay. Let's say this is S. These are the standard notations what I am telling you. It is unknown is represented by R, known one is represented by S. Okay. Then what we'll do, we'll connect a galvanometer from here. Fine. See. This is a galvanometer. And here it is not connected. Here this is a jockey. You can actually slide this jockey on this wire. Okay, what is jockey? J represents jockey. It is a metallic rod with sharp edge. Very pointed edge it will have. You can actually drag this on this wire. Alright. Then what we'll do? Now we want current to flow in this, so we'll connect this with a battery. We have connected it with the battery. This is the switch. Key K. Okay. These are the labelings. A, B, C, D. This is EMF E. K is the key. G is the galvanometer. J is the jockey. R is the unknown resistance. S is the known resistance. Clear? Draw this diagram. I hope you were drawing when I was explaining. No? Then draw it. Now, how do we find this unknown resistance? To find the unknown resistance, procedure I am writing, okay? To find unknown resistance, first what we'll do, find the null point. Find the null point. This is the null point method what we are going to do. Okay. How we'll find the null point? What null point means? Null point means basically is in this galvanometer it should show no deflection when I move this jockey. Okay. When I move this jockey, there will be one point where this galvanometer will show no deflection. What that will mean is that there is no current flowing in this particular wire. Correct? And that point is known as null point. Got it? We need to find a point in this wire, on this wire, where this galvanometer shows no deflection. That particular point is known as null point. So at that point, the current will not flow here, it will only flow in this particular circuit. Got the point? Now, let's say we got a null point here at D. Now, this particular length and this particular length, this entire length is 100 centimeter. Let's say this length is L. So how much will be this length? 100 minus L. Acha, can you see a Wheatstone bridge? I told you this is based on the principle of Wheatstone bridge. Can you see a Wheatstone bridge? No, right? It has 4 resistances. We have 1, 2. Where is the third and fourth? Basically, this wire is also having a resistance, right? That's why I told you select a wire where the resistance is not dependent on temperature, because the resistance of this wire is very useful to us. Now, let us assume, before this finding the null point, or let's say, let the resistance per unit length of the wire be R. Clear? R is the resistance per unit length. So if for unit length the resistance is R, for L length the resistance will be R into L. That means what I want to tell is this particular wire will be having a resistance. This particular wire will be having a resistance R into L. This much till this null point. And this particular part of the wire will also be having resistance. Now, the resistance per unit length is R. So for L length it is RL. For 100 minus L length, R into 100 minus L. The resistance of this side will be R into 100 minus L. Now can you see 4 resistances? 1, 2, 3, 4. And in the middle there is a galvanometer which shows no deflection. That means right now in this particular situation, it's a balanced Wheatstone bridge. Clear? After finding the null point, we have to find at what distance is the null point. The distance of null point from A is L. From here to here, this will be 100 minus L because this entire is 100 centimeter. So the resistance of this part will be RL. The resistance of this part will be R into 100 minus L. Now we'll find out this. See how. So this will be, let me make it like a Wheatstone bridge. Okay, here I don't think there is need to write that find the null point and calculate the distance. It's a common sense. If you're finding the null point, you have to calculate the distance L. Okay. Then this is, we have just assumed R. Okay. So now if this resistance is R, that is the unknown one. This resistance is S. This is R into L, this is R into 100 minus L, correct? This is connected to some battery. Anyways, that doesn't matter. And here there is a galvanometer, which is showing no deflection. Something like this we have. Since it is no deflection means balanced. Correct? Balanced means this upon this will be equal to this upon this. R upon RL is equal to S upon R into 100 minus L. Now see, R and R will be cancelled. What we have got? R is equal to SL upon 100 minus L. Note it down. Okay, from this one. R is equal to SL upon 100 minus L. Clear? L is in centimeter because it is 100. If 1 minus L is written, that means L is in meters. Done. Now see, always remember these are standard terminologies. This capital R is unknown resistance and this S is known resistance. But do not remember this formula. Why I am telling you, do not remember? Because if I change this then 100 minus L will come up, right? Sometimes unknown resistance will be given this side, known will be given this side. In question, sometimes known will be given this side, unknown will be given this side. So don't learn the formula. What you can learn is R upon this length is equal to S upon this length. Here, from here, no need to assume also. This we have assumed R, but it got cancelled. See, there is no R, small r in this question. We had just assumed. So from here, once you get the null point, your question is solved basically. This resistance upon this length is equal to this S upon this length. See, this resistance upon this length L is equal to this resistance upon this length 100 minus L. Now if I take this L to the other side, it will be R is equal to SL upon 100 minus L, the formula what we got. R upon L is equal to S upon this. Clear? So whichever side that particular resistance is there, that particular side's length you will take in the denominator. This side resistance, this side length. This side resistance, this side length. Clear? Easy, right? There's no need to do questions on this, because if you understand the concept, all the questions are very easy which are based on this. Okay, let us see one question. In the given meter bridge, the null point is at 30 centimeter. Find unknown resistance R. I hope you can do this on your own. What you have to do? This is given as 30 centimeter. 30 centimeter means this is how much? 30 centimeter. This is how much? 70 centimeter. Because it's a meter bridge. This will be 1 meter. This is 30, this is 70. Now what they have done is they have given this as parallel. If you solve it, you will get one resistance. This resistance upon this length is equal to this resistance upon this length. Question is solved. Over. Clear? Easy? You'll be able to do it? Let me just do it. If I resolve these two, this will be, let's say 1 upon R dash is equal to 1 upon 15 plus 1 upon 5. So that is 3 upon 15, 4 upon 15, 15 by 4. R dash is equal to 15 by 4, correct? 5, 15, 20, 15 by 75, 20. Correct only, right? 15 by 4. So now this resistance is basically 15 by 4. So this resistance upon this length, 15 by 4 upon this length, that is 30, is equal to this resistance upon this length, R upon 70. From here, okay, this 15 ones are 15, 15 twos are 30. This I can cancel. So this is basically 70 by 8. See, the 70 will come here. 70 by 8. 70 by 8 means 35 by 4. R will be 35 by 4 ohms. That is the answer. I hope there is no calculation mistake, but I hope you got the concept. Now see what they can do, how they can make this more complex. They can just give more combinations here of resistance. That's all. Rest, nothing they can do. They will add one more resistance here to increase the complexity. What you have to do, you just have to take the equivalent resistance. Maybe some complex combination they'll give here, some complex combination they give here, let's say. Fine. In that complex combination, here let's say they have given something like this, some like this, like this. Let's say this one is unknown. Still you can find it, because now you know this upon this is equal to this upon this. Some calculation will happen, you will find it. Clear? Try doing these questions on your own. Then let's go to the next thing, that is potentiometer. Potentiometer. From the name, as I told, potential, it is used to measure potential difference. It is an electrical instrument which measures potential difference more accurately as compared to voltmeter. So then we should not use voltmeter, we should use only this. No. See, this is something which is a big instrument. You cannot always carry it to measure the voltage. Voltmeter is something which is very small, very portable. you can take it anywhere and measure the potential difference. Okay, but if very much accuracy is needed, something is there where you have to measure it very accurately, we use potentiometer. Okay, mainly three different uses are there. Let's see. To measure the EMF of a cell, there is a cell, you don't know what is the EMF of it, put it in potentiometer, do some calculation, you will get the EMF. Okay, to compare the EMF of two cells are there, you want to compare the EMF, put it in potentiometer, you will get it, right? Anyways, if potentiometer is telling the EMF only, calculate both the EMF from potentiometer and take the ratio, you will get the comparison. Basically, this is not the main work is to measure the EMF. Questions based on this also comes, that's why I have added this also. Okay, then to determine the internal resistance of a cell, there is a cell, you don't know what is the internal resistance inside this battery, inside this cell, fix it in potentiometer, connect it to the potentiometer, do some calculation and you will get it. Okay, interesting, right? Let's see, in your lab also you would be doing it. How it is made, construction, a long wire is there. This time the wire is not 1 meter because the name is not meter bridge. Okay, this wire will be having some length L. It will be a long wire, maybe 1 meter, 2 meter, depends. It will be a long wire, it will be having some length L. And this wire will be connected to a battery. Now the wire will be similar, okay, where the temperature should not affect the resistance, it is made of alloy, all those qualities, all those characteristics are there. Okay, it's just that the length is not 1 meter. Now what happens, see, understand, to find the EMF and all those things, we have to connect that cell for which you want to find the EMF, connect it like this, there will be a jockey, all those things will come later, I'll explain you. But first understand why we use this, I mean what is the significance of this. If this is providing potential difference V, that means this side is V, this is 0. That's how we see. So this particular point, let's say, is at potential V. If this is at V, this point is at V, this point is at 0. From here to here, as we are moving, potential is dropping and ultimately it becomes 0. That means the total potential drop across this wire will be, total potential drop across this wire will be V, and this wire is of length L. For length L, potential drop is V. So for a unit length, how much potential drop will happen? For a unit length, potential drop will be V by L. So if I want to find potential drop at any point X, this is some point, I want to find how much potential drop will happen as I move from here till here. See, as we are moving, potential is dropping slowly, then only it is becoming 0. So at this point, potential will be something different, at this point it will be different, at this point it will be different. Every point the potential difference will be different, right? So till here, till X distance, how much potential is dropped, if I want to find. For L length it was V, for unit length it is V by L, for X length, V by L into X. Unitary method, simple, right? How beautiful is this? At any distance I want to find potential drop, multiply that distance with V by L. What is basically V by L? This V by L is represented as K. V by L, K is equal to V by L, that is potential gradient. For every wire there will be a potential gradient which will be given to you in the question. Potential gradient means how much potential will drop per unit length. Clear? So for X distance, if I want to find potential delta V at distance, let's say Y, delta V at distance Y, how much? Ky. Simple. If you know the potential gradient, multiply it with the distance, with the length of the wire, you will get the potential difference. Got the point? Note it down. Now, how do we use this particular method? This particular concept? First thing, to measure the EMF of the cell. So this is the thing which I have already told you. Now we'll connect a cell. This is the cell having EMF E. This is the resistance, internal resistance. And this is connected with galvanometer. This is a jockey again. It is not connected, it's a jockey, you can slide it over it. Now just make sure in meter bridge also, here also, while sliding, don't put a lot of force. What will happen? Cross section will change, right? If you just drag it, if you just slide it by putting force, somewhere the force will be more, cross section will reduce. Getting the point? The resistance will not be uniform. So just what you can do is keep it up, lift it and then put it, lift it, put it. That way you can do. Now how we are calculating, how we will calculate the EMF of this cell? See here, this is V. Here this will be V. Here this will be 0. Correct? Potential is dropping as we are moving from here to here. This EMF I don't know. It is an unknown. Some cell I have taken, I have connected it here. I want to find. What I'll do, first thing, find the null point. Null point means a point where the deflection in the galvanometer is 0, no deflection. Let's say that null point I have got here. Okay, and that particular distance is x. If the null point is here, the particular distance is x. Null point is at x distance from A. Clear? Here. Now we know if this galvanometer is showing 0 deflection, what does this mean? This point and this particular point are at same potential. Now see, this is at potential V. How about this point? When I am coming from here, there is no resistor, capacitor, nothing, no element is there in the middle, right? No electrical component is there in the middle. There will be no potential drop. Here also it will be V. Here it is V, here it is V. Here, since this is showing 0 deflection, whatever potential is here, the same potential is here. That means the potential difference in this from A to this J part, let's say some point D, J is jockey. From this A to D, whatever is the potential difference, the same potential difference will be in this particular thing. From this point to this point, same potential difference. And that potential difference will be the EMF of the cell. How? You will say, sir, R is also there. If the potential difference is between this, some potential drop will be for R also. That means the EMF will be different. Understand, if there is no deflection, that means there will be no current in this wire. No deflection means two things, right? One, the potential of this point and this point will be same. Second, there will be no current in this wire. I'll let's say A, B. This point I am taking as D. This point I'll take as C. Fine. Null point or no deflection means this particular thing. Since there is no current in this particular wire, this circuit is incomplete. See, this battery was connected from here to here to here. Now if I just cut it from here, Or if I remove this wire, this circuit is not complete. There will be no current through this battery. Got the point? There will be no current through this battery. Since there is no current, is there any current which will pass through R? No current will pass through R. And when there will be no current which is passing through R, the potential difference or potential drop across R will be 0. See here, I know what you are telling is that E minus IR it should be. The potential drop between this potential, it should be E minus IR, correct? Now if I is 0, delta V should be E minus IR. If I is 0, delta V is equal to E. That means the delta V what is there here, that is equal to the EMF of the cell. So if I get the delta V for this, the same delta V is the EMF of the cell. And what is the delta V for this? Kx, if the potential gradient is given. Got it? See, I'll write it also. Delta V is equal to, from here to here, VAD, or I'll write VAD. VAD, that is equal to Kx. Let's say the potential gradient of this wire is given K. K potential gradient. Or if it is not given, you can find out from this V and L. This will be V by L into X, correct? That is VAD. The same VAD will be across this also. E minus IR will also be, now, or I'll write, let's say this point is the some point F, fine? So here VFC is equal to E minus IR, or before that, VFC will be equal to VAD. VFC will be equal to VAD. And VAD is this. What is VFC? VFC is E minus IR according to everyone, right? VFC is also equal to E minus IR. See, understand, this we have got from no deflection. From no deflection. From null point. No deflection is the same thing. This conclusion we have got from no deflection. And this is something which we know, if this X, if I want to find potential at X, this will be VAD will be this, VFC will be equal to E minus IR, right? Now, since VFC is equal to E minus IR, since there is no current, VFC will be equal to E minus 0, that is E. VFC is equal to VAD. Since VFC is equal to VAD, that means E is equal to VAD. How much is VAD? E is equal to V by L into X. Clear? This entire thing, whatever I have written, is just to explain you. No current due to no deflection, okay? Note it down. Whatever potential drop is here, the same is the EMF of the cell. That is the main concept. This anyways I have written in the next page. Fine. Now, what you have to note, two important points here. One, the polarity of this particular battery and this cell, it should be same side. If here it is this bigger plus positive one, this side also it should be higher potential. Polarity of the battery and the cell should be same side. Note, important. Polarity of battery and cell should be same side. Clear? Second, the potential drop across this entire wire should always be greater than cell. See, basically what is written in the book, I'll tell you. In the book it is written, the voltage of this battery should be greater than the EMF of the cell. What is written is, V should be greater than, write in a different color. V should be greater than E. This is written. But what does this mean? Why it is written? Basically, the potential drop across this complete wire should be greater than E. Why? Suppose potential drop in this wire is 10 volt, let's say. That means, let's say this battery is 10 volt. So here it will be 10, this point. Okay, this point will be 10 volt. This point will be at 0 volt. Correct? Now let's say the cell which you have connected is having more EMF. It is having 15 volt. So if this is having 15 volt, will you get a null point between this? Never. Let's say this is having 5 volt. Clear? Now if this point is at 10 volt, slowly I am coming, potential will be decreasing. And then ultimately it becomes 0, right? So here 10, 9, I moved some, it became 9, then 8, then 7, then 6, 5, 4, 3, 2, 1, like that. 5 volt is there in between. So that's why if this EMF is 5 volt, wherever there will be 5 volt, if I connect this jockey there, this will give me 0 deflection. Correct? But if this particular cell is having 15 volt, in between this, there is no point where the potential is 15 volt. I cannot get the null point here. It will be outside of this wire. I mean, if the wire is long, wire has to be long. There is no point if this EMF is greater than this. That's the reason in books they have written this battery should have more potential than this cell. I hope it is clear to you now. Okay. What you have to write? But what I am telling you, or you can write both the things. V should be greater than V should be greater than E. Or if you want, you can write potential drop across wire should be greater than E. This is the main. Why I am telling you this? Maybe if there is a resistor connected here, a big resistor connected here, right? Let's say there is a cell or something which is having battery having potential 10. Here a resistor is connected. Some drop happened here. So at these two ends, the actual voltage will be lesser than this, right? And here whatever we see, this V by L is not basically V by L. This is the potential drop across this, not this battery. Don't see this. Always see these two ends. Fine. Here just because there was no other resistor, that's the reason it was same. I hope you are clear. So if you write this, potential drop across wire should be greater than E. People who want conceptual knowledge, for them I'm telling potential drop across wire should be greater than E. Normally you can keep in mind for boards level V should be greater than E. Next, to compare the EMF of two cells, if it can tell the EMF of one cell, you can take out the EMF of two cell and compare it, right? But there is a way of doing it. See. So now first it was this, then now we have connected two different cells like this. This is E1, this is R1, this is E2, this is R2. They are two keys. What we'll do? First, we'll connect this key first. K2 is open, or let me write as K1 is closed. K1 is closed, K2 is open. Okay. So when we do this, then obviously whatever we did in the previous one, the same thing I have to do. If this is closed, then we'll find the null point. Find null point. Let's say the null point is at L1. Null point L1. Here I have connected for J1. The null point what I got is L1. Okay. So what will be the EMF of this particular cell? E1 will be equal to C. Null point means there is no current. There will be no potential drop across R1. So E1 will be equal to V by L into L1. KL1. Okay. Second, what we'll do? K2 is closed. K1 is open. Again, find null point. See here. Now we'll open this. We'll close this. So this battery will be connected. Then again for this cell, there will be different null point because the EMF will be different. So now let's say second null point we got somewhere here, J2. And this point is L2. So E2 will be equal to V by L into L2 or KL2. Just compare, divide both of them. E1 by E2, V by L L1 divide by V by L L2. E1 by E2 is equal to L1 by L2. Done. Compare. Done. If you know the EMF of one cell, you can find the other one also. See, let's say I know the EMF of E2, I want to find E1. I'll take this E2 to the other side. Simple. So it's the same thing what the first one was there, finding the EMF of cell, comparing the EMF of cell. Easy. Next, to determine the internal resistance of a cell. Now see, this is good. So this was the setup. Then right now what I'll do is, I'll connect a cell and I'll connect a resistance. This resistance is known. We have to find internal resistance. So which is unknown? This one. Internal resistance means internal resistance, a cell will only have internal resistance. So we have to connect a cell. This is a cell what I have connected. This is a cell what I have connected. This resistance is inside it. It's internal resistance. Now, how to find this? See here. First what we'll do, first we'll find the EMF E. See here. For finding the EMF, we'll just see the no deflection here. First, find null point. Okay, here null point at L2. I have not written, write it down. Okay, find null point. Let's say I have got the null point at some point L1. Okay. Null point is at L1. Clear? We got it. Now from there what I'll get? E. E is equal to V by L into L1. That we already know. How to find the EMF? This L1 we got from the null point, and then the potential drop across this and across this will be same, since there is no current, because there is no deflection. The drop across this will be zero. Whatever will be the potential drop here, the same will be the EMF of the cell. That's how we got E. Second, now connect or close the key. Close key K. On closing, what will happen? Understand. Interesting. If I close this, the current will start flowing in this. And this null point will also change. Why this null point will change? Because now since the current is there in the circuit, since the current is there in the circuit, there will be a potential drop across this also, across this also. That means at these two ends, the potential drop will change. So the null point has to change. Because the null point is basically not the EMF of the cell, it's basically the voltage between these 2 points, correct? Null point will change. Current will flow. Null point will change. Find new null point. Clear? Now let's say we have got the another null point somewhere here. J1, J2. Oh, no need for this. So here, this is at L2, right? So now, new null point is at L2. From this null point, what we got to know? The potential difference of here we can get to know. We got, right? So that will be the potential drop across this. Let's say the current I is flowing in this. I'll tell you how to find the current I also. If current I is flowing in this, potential drop across this particular thing will be E minus IR. So from here, E minus IR is equal to this, is equal to this. The potential from here to here, L2. That is V by L into L2. Fine. Now we have to find I. How do we find I? Just see here. Since there is a null point in this, there will be no current which will be flowing from here to here, correct? There will be a null point here. There will be no current which will be flowing from here to here. The current is only flowing in this circuit. Since the current is only flowing in this circuit, I know this resistance. Can I find the current? This will be, for current, I will be equal to E upon R plus R. Arey bhai, this entire circuit, these two will be in series. Because there is no wire, here there is no current. These two will be in series. So total resistance in the circuit is capital R plus small r. Current is total voltage upon total resistance. So that is E upon R plus R. This, if I substitute here, I'll get my answer. See how I'll do is, now it's just substituting. Okay, this is one equation, main, and this is one. Now I'll just substitute. This V by L into L1 I'll substitute here. Okay. This, let's say 3R. This, if I substitute, I am just substituting now. This E will be V by L into L1 minus this I is E upon R plus R. Acha, let me not substitute E first. E I will substitute at the end. E minus E upon R plus R. There are easier methods also to get the answer. I am doing it from this. E minus, I have substituted this, then this R is also there, is equal to V upon L into L2. From here, this will be ER minus ER minus ER. Sorry, plus. This R will be multiplied, ER, this R will be multiplied, plus ER, and this is minus E into R. That is equal to V by L into L2. This ER will be cancelled. ER is equal to V upon L into L2. Okay, see here. ER, it is written here only, is equal to V upon L into L2. What is E? V upon L into L1. So V upon L into L1 into R is equal to V upon L into L2. Wait. Acha, this R plus R will also get here, go here and multiply, right? R plus R. 1 second. I'll write it properly. ER, this was multiplied here, this will go and multiply here also. See from here again. ER plus ER minus ER is equal to V upon L L2 R plus V upon L into L2 small. Correct? I have just expanded it, multiplied here and expanded. This ER will be cancelled. So from here, ER is equal to this. E I will substitute from V by L. So this will be V by L L1. E I have substituted V by L L1 into capital R. That is equal to V by L L2 into R plus V by L L2 into small r. V by L L2 into R plus V by L L2 into small r. Now see here. This V by L is common. Right? From here, RL1 is equal to RL2 plus small rL2. From here, if I take this side, R common, L1 minus L2 is equal to small rL2. From here, small r I need to find out, internal resistance R, L1 minus L2 divide by L2. That is, R is equal to R common L1 by L2 L1 by L2 minus 1. Clear? This formula you can remember. this formula you just have to find two null points. That's all. Whatever I have done was to just show you how to get to this particular formula. Just find two null points, take the ratio, subtract it from 1, multiply into the known resistance. You will get the internal resistance. Got the point? I hope you understood how to do this. Try doing it on your own. Try getting this formula on your own. All the derivations what we have learned today, try doing them on your own. Clear? Alright. So today we have seen meter bridge and we have seen potentiometer. How meter bridge is used to find unknown resistance, that also we have seen. Then how potentiometer is used to measure the EMF of cell, compare the EMF of two cell and find the internal resistance of any cell. Right? In the next session we will be seeing numerical problems. The chapter is almost over, only 2 sessions, and then we'll begin with a new chapter. Alright? I hope you liked today's session. If you liked it, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright? You can visit our website www.v-learning.in. All these sessions you will be getting over there also. Along with that you will be getting lecture notes also for each and every lecture, which will help you a lot. Okay? Do visit the website. We'll meet up in the next session. Till then, keep learning from V Learning. All the best.